One of the chief particles we use in chemistry to explain things is the electron. And the diagram here simply shows us what we think it looks like. And now you should be able to see with the fuzzy blue thing, we should be able to see that maybe you can understand why people think or call the areas where we find electrons clouds. But each of them are energy levels, and as we go through, hopefully a bit more will be explained and it'll become clearer to you. It's probably easiest if we review. And way back when, we learnt that electrons have a negative charge. And this was done by Thomson, and he basically fired electrons through between charged plates and saw they were attracted to the positive charge and repelled by the negatively charged plate. The crazy thing is, though, electrons are so tiny. They're really small. We say they're around about 2,000 times smaller than a proton. Now, a proton is really tiny, so electron is super tiny, if you like. But the crazy thing is, on this super tiny particle, we've got the opposite and equal size charge as that on a proton. So they have a very large charge to mass ratio, much larger than the proton. The idea, as I've said, came from the work that Thomson did, and the tube shown here, the cathode tube, is basically what he was using, and the charged plates, as we can see, the deflecting plate actually causes it to bend towards the positive. This tells me it's got a negatively charged, and we have used this in the old days when the first televisions came along and the first cathode ray tubes, oscilloscopes and tubes came along. They were based upon this very principle, with a screen that would fluoresce when the electrons hit it on the inside, and that was basically the way things worked for many years. But we know now that electrons can get very excited, and when they get excited, they don't like it. Like anything, when you have too much energy, you try to get rid of it. Now, electrons release their energy in the form of photons. Fancy word, but really it's a simple thing. A photon basically is a piece of radiation that has a fixed energy associated with it. Right? So the more energy, the different type of photon, the different type of radiation. And more about that in subsequent little presentations. The most amazing part for us, though, is that these different photons produce the different colours. The colours of the rainbow we see are caused by, or fireworks that we watch, are caused by different atoms having different electrons move different amounts of energy or lose different amounts of energy to produce the different coloured lights. And it's quite amazing that a lot of the stuff we don't actually see. If all the atoms in an element move, then we can create all of the electromagnetic spectrum. So all the way from gamma rays all the way through to microwaves. And this presents its problems in itself, but our eyes only detect that small part of the electromagnetic spectrum, which is to do with light and colour. The idea that the energy levels were in fixed positions first came to us when people were able to break the spectrum apart. Now, when we break the spectrum apart, sometimes we see a bright line, other times we see a dark line spectrum. Now, for any particular atom, that position, or that wavelength, if you like, is in the same spot. So it's like a fingerprint for a particular atom. And scientists have used this idea for quite a large amount of time, and it's very important for astronomers, because they can actually work out what chemical composition of stars are based upon the spectra that we get. Now, each of those lines corresponds to a jump of an electron as it falls back and releases energy. Probably the easiest way for us to illustrate this is to have a look at this imaginary electron. So I'll just drag an electron in. And we can see now I've put it at this bottom one called GS. GS stands for ground state, or the position the electron would occupy under normal conditions. Now all the ones above that, all the lines above that, correspond to subsequent energy levels it could exist on if it had the right amount of energy. And we know that each one away from the ground state, so 1 requires the electron to have more energy than the ground state, 2 requires more energy still, 3, 4, 5, etc. They require more energy as we go to get for the electron to move to them. Now this explains why electrons do it. So if we excite an electron in a chemical reaction, or hit it with some heat, or provide it with some light energy, or any other form of energy that's able to absorb, it will jump to the energy level that corresponds to the energy it's absorbed. But it doesn't like being there. It's much happiest on its ground state. So therefore it will then try to move there and lose the energy it has. Now some people might have noticed that the energy levels get closer together as I get further away from my ground state, and this is what we think is true, and this is the way I would like you to draw it in a question in paper 2. I'm sure there'll be a paper 2 question on it. But let's say our electron gets so much energy it jumps to here. In other words, it's got more energy than the infinite one. Now in this case, my poor old electron is no longer being attracted to the nucleus anymore. And if an electron gets to this position, it is going to leave the atom with one less electron. In other words, we're going to form a positively charged ion. And so if the electron gets there, it escapes and goes and is used by some other element or some other atom in the thing.